Okay, so we'll move on to question number 16, exercise 4B. So we'll practice a few more sums with horizontal circular motion. They say a fairground consists of a vertical hollow cylinder of diameter 5 meter, which rotates about a vertical axis through its center. What's happening? You have a vertical hollow cylinder, okay, and diameter 5 meter. It rotates about a vertical axis, right? So basically, you have a hollow cylinder. It's vertically there, so like this. So this is hollow. Hollow means inside is completely empty. And so this is the axis of the cylinder, right? Mainly when they say vertical axis, this is what we mean by vertical axis. Diameter is 5 meter, which means radius is 2.5 meter, right? Which rotates about a vertical axis through its center when the ride is rotating at W radians per second. So basically, this is the cylinder is rotating about its axis. Can you understand? So about the axis, the cylinder is rotating. Okay, so the cylinder rotates about this axis. Okay, so the whole cylinder is, spinning about the axis. When the ride is rotating at W radians per second, so at W radians per second, it's spinning the cylinder about the axis. They say the flow of the cylinder opens, okay, without slipping. The people on the ride remain in contact with the inner surface of the cylinder. Okay, what's going on? So this is actually a fairground ride, right? So which means this is something that you find in a fair. So in a fair, it's a ride. So basically, people get on this ride, and then when they get on the ride, the cylinder starts to it starts to spin, right? It starts to rotate. It starts going in horizontal circular motion, and basically, what you have is you have people inside, right? So there are people inside, and what they're saying is, when the people are inside, and once the cylinder achieves a certain, uh, a certain angular velocity, once it achieves a certain angular velocity, they say the flow of the cylinder opens. Basically, the people stand on the floor, right? So the people stand on the floor. What happens is the flow opens, but they say the people are not going to slip down. They're not going to slip down. The people on the right remain in contact with the inner surface of the cylinder. Basically, all those who were in the cylinder are now pushed onto the inner surface. Basically, they are over here. Okay, everyone is kind of like resting on the inner surface of the cylinder. They're asking you, without slipping, people on the right remain in contact with the inner surface of the cylinder, given that the coefficient of friction between a person and the inner surface of the cylinder is 2/3. So basically, you have friction here. It's a rough surface. Find the minimum value of W. Okay, so W is the omega, the angular velocity. Okay, so what do we have here? So let's consider one person. Okay, so I'll consider one person as a particle. So this is where the person is. Okay, so this person, I hope you guys can understand how this occurs, right? Because when you reach a certain, when this starts spinning a little bit fast, you can understand that the person is kind of like pressed against the wall, right? He's pressed against the wall, so he's going to actually be pushed against the wall just because of the circular motion. So he doesn't need any support in his feet. Okay, so this is the person. The flow is now open, so which means it's like basically in air. Okay, but here just because it's spinning, the circular motion of the forces are keeping him in. They're keeping him over here. So this person is rotating in a circular motion, right? So this is how the rotation looks like. So the cylinder is rotating. So this person is rotating on this circle. His center is here. Okay, so for this person, his center of the circular motion is over here. Okay, because he is going in a circle like this. Okay, as the cylinder rotates, as the wall of the cylinder rotates, he is also moving with the wall, right? Okay, so then what are the forces that you have here? So the forces you have here, number one, you have the weight, right? So we have the weight of the person. Let's mark it as mg. So we have the weight of the person acting down, and they very clearly say this is a rough cylinder, right? If this is a rough cylinder, what else do we have? Obviously, that's why they say this is a rough cylinder, right? So basically, if the weight is acting down, another reason why this person can stay like this is through the support of the friction. So the weight is acting down. The friction is what's preventing this person moving down. The friction together with the circular motion. Okay, so this is what prevents him from moving down. So upwards, you have the friction. Okay, so they want the minimum value of W. So basically, this is the friction. Okay, and then what other forces do we have? So think about this. Are there more forces? Okay, so then so you have the friction acting upwards and it's the weight acting downwards. And remember, there are no ropes or any other support for the person. They don't mention any such thing. So it's basically the circular motion that the cylinder spinning fast, okay, is what pushes this person against the wall. So when this person is pushed against the wall, there's another important force here. Basically, you need to identify what's the centripetal force. As I told you, centripetal force is not a force on its own. Like someone acting towards the center, and that force we name it as a centripetal force. Okay. So over here, I think you can see because the person touches the wall, there's a contact force. So basically, it's the normal reaction. It's the normal reaction who is acting towards center. So in this case, normal reaction will be the centripetal force. Okay, so our force diagram is complete. All you need to do now is what? In horizontal circular motion, you just have to do two things. Always in horizontal circular motion, you have vertical equilibrium. Vertical forces are always in balance. And the other one is you apply F equal ma towards the center. So let's go for vertical equilibrium. So in vertical equilibrium, what do we have? So if the person, basically they are saying given that the coefficient of friction, okay, they want to find the minimum value of W, right? Okay, so basically we need to go with not just the normal friction, but with the maximum friction here, right? Because they want the smallest value of W. I'll tell you why that works out like this, okay? So we'll go with the maximum value of friction. The maximum friction is equal to the weight because obviously these two guys are in balance. For the vertically forces must be in balance, right? So your the friction, upward friction must be equal to the downward weight, right? Because they are vertical forces. I told you vertically forces must be in equilibrium, right? So and then we can, so F max, okay, let's apply F equal ma towards center also. F equal ma towards the center. Okay, so what are the forces towards the center? So if you consider this object and consider forces towards the center, so you can see normal reaction is acting towards the center, right? The normal reaction is the only force acting again towards the center. There's no one supporting it or opposing it. So normal reaction equals ma. So mass is m and acceleration. You remember acceleration is the centripetal acceleration, right? Not just any other acceleration. So centripetal acceleration, we had two forms, v square over r and r omega square. So in this case, because we are trying to find omega, right, W, okay, the angular velocity, we will go with R omega square. Okay, so normal reaction equals M and radius. Guys, radius over here for the cylinder, I mean, this person is moving in a horizontal circle of radius 2.5, right? Radius 2.5 into W, so omega was W. Agreed? Okay, so, okay. Let's try to find the value of W. And guys, one more thing. So why did I use the F max here? Because the reason you need to understand why we go with the F max is because they say that now they're asking you to find the minimum value of W, right? The minimum angular speed. So you need to realize that that it's the speed, it's the rotating speed that decides, like, how much this person is, contacting the surface. So basically, if you rotate at a really high speed, this person is pinned tightly against the wall, giving a higher normal reaction. Right. So if it is, now they say the minimum value, so which means like the smaller speed that you need to rotate in order to keep this person. So if you go at the small, the least possible speed, what you need to realize is, so it's the speed is, now you need to, you know that the higher the speed, the more secure you are, right? The more secure you are on this wall without falling. But the slower, I mean, if you're trying to go at a minimum speed, you need to realize that you have a risk of, slipping down. Yeah, like you have it's like almost in a limiting equilibrium. That's the point here. So if you are going at the minimum value of W, you are in limiting equilibrium because, and that's why you have the maximum friction. Okay, but if it was rotating at a higher speed, the normal reaction would be higher and your friction doesn't need to be F max, because in that case you are in equilibrium and you don't have a risk of, slipping down. But just because they say you're going at the lowest possible speed where you can maintain this, which it means you are in limiting equilibrium. So you are almost and not about to, it's about to slip. So that's why we go with F max. Okay, so now let's find the value of W. So F max is equal to mu R. Mu R is mg. So over here I have R is mu is 2 over 3. 2 over 3 R equal mg. So capital R equal 3 over 2 mg. Right? So this is the normal reaction. Input the normal reaction over here. And you can find the value of W. Right? So we can substitute 3 over 2 mg. M into 2.5 into W square. So you can see we really don't need to know the mass of the person, right? Because cancel, M cancels out. So we get here 3 into G divided by 2 is down anyway into 2.5 equal omega square. So omega is root of this. Okay. All right. So this is the minimum value of W. So this is the W minimum value. Let's get the answer. All right, so you can simplify this and just recall that G is 9.8. If you input G as 9.8 and give the value of W, you should give it to 2SF or 3SF if you want to give the answer in exact form. So sometimes in exams, they might ask you exact answers, or they might ask you, if they ask you exact answer, then exact answer should be given in terms of G. So if you're trying to go for an exact answer, then you type 3 over 2 into 2.5. Okay, 3 over 2 into 2.5. So if you type that inside the root, I think you get root 15, right? Root 15 over, how much was it? Root 15 over 5, right? That is the answer you get if you type this inside the, if you type it in the cal. Okay? And so if you type it inside the cal, you get root 15 over 5. And remember the G is still inside the root. Okay, so this is just, the part about typing in the cal. Basically, let me show like this. Okay, basically, if you do it from your head, 2.5 is 5 over 2, right? 2.5 is 5 over 2. So basically, the 2 and 2 cancels here, and you have 3 over 5, right? 3g over 5. So root. And then if you rationalize this with the root 5, that's where you get root 15 over 5. Okay, so that's where you get root 15 over 5. Okay, so if you rationalize, it's root 15. The g also should be inside the cell. Okay. Okay, so this is the value of W, and if you give the G as value as 9.8, you can also give this answer to 3SF, right? So 3SF or 2SF. 3SF answer is 2.42 radians per second. So this is the value of W. Okay. Why would someone call me? In the normal call, they are calling me. And you can write if the speed, if the speed reduces, the name this is, I think this reason is enough. Shall we move on then? I think